Hello, in this video we're going to talk about neutralization and titrations. So up here at the top we've got a summary of what a neutralization reaction is. It's an acid-base reaction. It's something we call a double displacement reaction, and it follows this general format here where you've got two compounds coming together. We'll call them A, B, and XY. And the first element in those compounds trades places. So now X is going to pair with B and A is going to pair with Y. They call that double displacement because you've got two things displacing each other. So they're switching places is what's happening here. So they're going to switch places. Alright, so the first type of question you might see on this would be just a straight balancing question. So this goes back to Unit 4. If you want to, it's good to review these topics before the final anyways. So remember, our technique for balancing is we can make a little T-chart here, and we can count the number of atoms on each side of the equation. So I'm going to count my hydrogens, I'm going to count my sulfates. So that's a polyatomic ion, so I can treat it as like one thing. I'm going to count my aluminums, and I'm going to count my hydroxides. So on the left, I have two hydrogens, I have one sulfate, I have one aluminum, I've got three hydroxides. Alright, over here on the right, I have two aluminums, I've got three sulfates, and then, oh, it looks like I don't have any hydroxide over here, I've got water. Here's where it becomes helpful to think of water as being made of HOH. So remember when we acted out these reactions, we paired together an H and an OH minus to make water. So think of water as being one hydrogen and one hydroxide. So then we go to counting, we can say, okay, one water is one hydrogen and one hydroxide. Trust me, it'll make the balancing here easier. So then I'm going to pick one thing that's not balanced that I want to balance. So how about sulfates? That's pretty out of whack. I've got one here and I got three over here. So I'm going to put a 3 out here in front. That will give me 3 sulfates. It will also give me 3 times 2. It'll give me 6 hydrogens. So let's balance the hydrogens next. Let's go over here and put a 6 out in front. That gives me 6, that gives me 6 hydrogens and 6 hydroxides. Sorry, that's supposed to be a 6. That got kind of messy. So now let's look at our aluminums. Let's put a 2 over here, so that'll give us 2 aluminums, and then 2 times 3. Now I've got 6 hydroxides. And look at that, everything is balanced. Alright, let's do one more of these right below here. So again, let's tally my calciums, my hydroxides, my hydrogens, and my bromines. So over on the left, I've got 1 calcium, 2 hydroxides, 1 hydrogen, 1 bromine. Over here on the right, remember, I'm going to think of water as being HOH. So I'm going to say on the right, I've got 1 calcium, 1 hydroxide, 1 hydrogen, and 2 bromines. So let's balance the things that aren't balanced. Okay, let's try and balance my bromines. I want 2 bromines on the left, so I'm going to put a 2 out here. That's going to give me 2 bromines. It's also going to give me 2 hydrogens. So now my hydrogens and hydroxide are not balanced, so let me put a 2 over here. That gives me, sorry about that, that gives me 2 hydroxides and 2 hydrogens. And look at that, I am all balanced. So again, our tricks for balancing would be 1, make a T-chart and tally. And then a related tip is treat water like it is hydrogen hydroxide. So every time you see a water, think of it as 1 hydrogen and 1 OH. And that will make your balancing easier with this type of reaction. Okay, so the next kind of step here, here's another related one, vocabulary, acid, base, and salt. So let's go back to one of these ones. This molecule right here is going to be my base, and I'm going to recognize that because of the hydroxides. So bases are things that tend to make hydroxide. This one right here is my acid, and I recognize my acid because it starts with a hydrogen. And then I'm always going to make water in these neutralization reactions. And by definition, the thing that I make that is not water is called a salt. So in reaction 3, iron chloride is my salt. Down here, you can see here's my water. So the product that is not water is my salt. So in this case, it's potassium carbonate is my salt here. Okay, so that's a little bit of vocabulary. Remember, we can scroll back up here to this definition to look at what it means to be, salt in a water. All right, so now let's scroll down to the next type of question. This would be, you're going to have to predict the products first and then balance, okay? So when we're predicting the products, remember, in this type of reaction, these first elements are switching places. So hydrogen and lithium switch places. So lithium is going to pair up with phosphate, and hydrogen is going to pair up with hydroxide, and this is water, right? HOH is water. When we are putting together these other compounds, we have to think about the charges here. So if we were to look at phosphate, we would say it has a -3 charge. If we look at lithium, it's got a +1 charge. How do I know this? Lithium, I can look up on the periodic table and see that it's in the first column. That means it's a +1 ion. Phosphate, you do not have to memorize the polyatomics. You'll be given a list of them and their charges. Okay, so you'll just be able to look that one up. And then we do the crisscross method and we say, okay, I'm going to put a 1 there, I'm going to put a 3 there, so let's rewrite it. It is going to be Li3PO4. So this is my overall reaction. So it is H3PO4 plus LiOH makes Li3PO4 and H2O. Then I'm going to do step 2, which I'm running out of room here, where I'm going to do my T-chart and I'm going to tally. And I'm going to notice, for lithium, I've got 3 lithiums on the right. I've only got 1 lithium on the left. So I'm going to come over here and I'm going to add a 3. Okay, so now I'm going to have my lithiums will be balanced. Oh, but now my hydrogens are not balanced. I've got 3 hydrogens over here and only 1 over here. So let's come along up here and put a 3 right there. And now I am balanced. Another way you can think about this is you know that your H3PO4 has 3 H's in it. So how many OHs will it take to react all your hydrogens? Well, I'm going to need 3 of them. So that's why that number right there is a 3, because I need 3 hydroxides to react with my 3 hydrogens. Okay, if we draw this out like we did the other day, the reason why lithium and phosphate combine a 3-to-1 ratio is because phosphate looked like this. It had 3 spots to combine with because it had a -3 charge, and then each lithium looked like this. It just had 1 little triangle, so you need 3 lithiums to pair with your 1 phosphate. So that's what this subscript is telling you, is how many of those things are found in your compound. Okay, so let's scroll down and do one more here that we have room for. Let's look at number 9. So I am going to, my first elements are going to switch places with each other. Sorry, my pen's being a little sensitive right now. So my iron is going to go with the sulfate, and my hydrogen is going to go with the hydroxide. So that's water. So you always make water. That should be a gimme. And then the other ions are going to stick together. This one's actually a little tricky. Okay, so this one, let's look at this iron over here. I've got 1 iron combined with 3 hydroxides. So the charge of iron in this case must be +3, because it takes 3 hydroxides to stick with 1 iron. So it's kind of like that other diagram we were just looking at here. Oh, that's a bad picture. Anyways, we need 3 hydroxides for 1 iron, so iron must be +3 charge. Okay. This is kind of a trickier one. Sulfate, polyatomic ion, you don't have to memorize those charges. They will be given on your equation sheet here. But what you do need to do is know how to apply this and do the little crisscross method here. So the formula of my salt is going to be Fe2SO4 3. And I'm going to make water, and my reactants were H2SO4 and FeOH3. So one thing you might notice is that, okay, there's 2 ions over on this side, so I'm going to need 2 irons on this side. Okay, and notice now I have 6 OHs over here, so I'm going to need 6 OHs on this side. So I'm going to turn this into a 6, because remember, we think of water as being like HOH. Okay, and now I need 6 H's over here, so I'm going to put a 3 in front of that. So now it gives me, now if you look over here on the left, I'm going to have 6 H's and 6 OHs. And that's what you should end up see happening in these neutralization reactions, is your number of hydrogens and hydroxides are equal. That's what makes this solution over here neutral. Okay, is because your hydrogens and hydroxide have reacted with each other to make water. Okay, so number 9 was a little bit of a trickier one. 10 is more straightforward because they're all positive, negative 1 charges. Okay, let's scroll down and find a titration calculation. So this is like we did in class the other day, where you're going to collect some data and figure out how much base it takes to neutralize a certain amount of acid or vice versa. And it's basically a stoichiometry problem. So let's kind of walk through the steps here in this type of problem. So you're going to have some sort of sample of acid. So right here we've got 60 mils of HCl, that is my acid, and you're going to add to it 45 mils of 0.2 molar NaOH. So this is how much base it takes to neutralize the sample of your acid. And you know that when all of your acid is neutralized, that means your amount of H is equal to your amount of OH minus. Okay, so we'll come back to the idea. So first we want to figure out how many moles of NaOH we added here. So we know that molarity is moles per liter. We can rearrange that to say molarity times liters equals moles. So let's find our moles of base added to our solution. So we had 0.2 molar base, and we had 0.045 liters of base. So I'm going to take this milliliters and divide it by 1,000 to get liters. And then we're going to plug that in our calculator, and we will say 0.2 times 0.045. That means we've added 0.009 moles of NaOH. Okay? And then we can look back at our balanced chemical equation. This tells us the ratio of acid to base. So it's like we were talking about in class the other day. Is it a 1-to-1 ratio, 1-to-2 ratio, a 2-to-3 ratio? In this case, it is a 1-to-1 mole ratio. I find that by looking at the coefficients here in the balanced chemical equation. If there's no coefficient written, we assume it's a 1. So there's a 1-to-1 ratio of acid to base. So if it took 0.009 moles of NaOH to react all my acid, for every 1 mole of NaOH, I react 1 mole of HCl. So it's a 1-to-1 ratio, so I must have had 0.009 moles of HCl in my beaker. Okay, this ratio refers back to what I was talking about up here anyways. Okay, so we got this many moles of HCl in my beaker. Now let's convert that into molarity. So they told us up here in the problem that we had a 60 mil sample of HCl. So I had, if I look at my molarity equation here, I had 0.009 moles of HCl, and my volume was 0.06 liters, because I have to, remember, divide my milliliters by 1,000 to get liters. And if I do that, 0.06, I will end up with a molarity of 0.15. So I just used titration to figure out the concentration of my acid. It is 0.15 molars. So step 1, figure out the moles of stuff you added. Step 2, use a mole ratio to convert from moles of base to moles of acid. And then step 3, use your molarity equation to use moles and volume to find molarity. Okay, let's try this one more time here. This time we've got a reaction where it's not a 1-to-1 ratio. It looks like it is a 1-to-2 ratio. So we'll want to pay attention to that later. Okay, so in this case, you are trying to, you got a sample of sulfuric acid, 75 ml sample, and you find that it takes 50 mLs of 0.3 molar sodium hydroxide to neutralize your sulfuric acid. So we're going to follow the same steps here. So step 1, figure out the moles of base you added. Okay, so molarity times liters, so that's 0.3 molarity. My liters is 0.05. Because remember, I got to divide my milliliters by 1,000 to convert it into liters. So that's 0.3 times 0.05. That is 0.015 moles of NaOH. Okay. So let's use that to figure out the moles of sulfuric acid. So 0.015 moles NaOH. And if I look up here at this ratio here, for every, it takes 2 moles NaOH to react with 1 mole H2SO4. That is my mole ratio that I'm finding from the balanced chemical equation. These are the coefficients from the chemical equation. It makes sense this is a 1 to 2 ratio because the sulfuric acid has 2 hydrogens in it, so you're going to need 2 hydroxides to react with those 2 hydrogens. So I'm gonna multiply 0.015 times 1 divided by 2, and I'm gonna get 0.0075 moles of H2SO4. Okay. Now my last step is I know how many moles of H2SO4. That's this right here. I know the volume. Let's look back at the problem. I forgot what it was. The volume was 75 milliliters. Okay. Remember, I need to convert that into liters by dividing by 1,000. 75 liters. So my molarity is going to be 0.0075 moles divided by 0.075 liters. So it is going to be 0.1 molar. So that is how we do a titration problem.